Before we continue with more examples and the next theorem, which is Stokes' theorem, I want to give some more remarks about the divergence and some related notions and a bit of intuition, and I think this is important stuff. So remember that the divergence, or what we denoted either like this or like this, is just the sum of the partial derivatives of the components of f with respect to the variables x, y, and z. And note that this definition requires f to have partial derivatives, or in general to be C1. And in addition, it's dependent on the coordinate system. Okay? It's defined via x, y, and z. So now that we know Gauss's theorem, which I left only the formula down here, I erased all the details of the theorem that have to be verified before the formula holds, we can actually give an alternative definition of the divergence, which has two advantages over this definition. One, it's independent of the choice of the coordinate system. And two, it doesn't require f to be C1. It doesn't involve derivatives. Okay? The reason that I started out with this and that's the way I introduced it is because this is the more useful one. This is what is usually used in calculations, in applications. The definition that I'm going to present now is more of a theoretic nature, but it just shows you that the notion of the divergence is not dependent on the field being C1 and is not dependent on the choice of the XYZ coordinate system. So, given, so this is going to be remark 1. Given a point P, some point in three-dimensional space, I want to define the divergence at the point P. And the way I'm going to do it is the following. Take a ball with radius r and center P. A ball with radius r centered at the point P, denoted VR. That's going to be the ball. And the sphere, which is the boundary of this ball, with boundary, the sphere, let's call it SR. Okay, so VR is a ball centered at the point P with radius r, and the boundary, the sphere, is going to be called SR. Now, according to Gauss's theorem, which we now know holds, and in order to write it, we don't need to go back to the definition of the divergence. According to Gauss's theorem, by Gauss, the double integral, the surface integral over SR of our given field equals the triple integral over VR of the divergence. I just rewrote Gauss's theorem, replacing S with SR and V with VR, the specific ball and boundary sphere. Okay. Now, this I can rewrite. So this is a triple integral over a domain of some scalar function. I can erase Gauss now. We had a theorem, I think we mentioned it for double integrals, but it's true for triple integrals, just like it was true for regular definite integrals with one snake. And it's called the intermediate value theorem for integrals. If you have a function and you're integrating over some domain, that equals the volume of the domain times the value of the function at some intermediate point. So this equals the value of the function here is the divergence, that's the function we're integrated. The value of this at some point, let's call it Q, at some point, which lies inside the ball, times the volume of the ball. Let's rewrite this here. Equals the value of the function at some point Q times the volume of the domain. So this is the intermediate value theorem for integrals, and in this case for triple integrals. Is it clear? Is the statement clear? Okay. The value of the function at some point in the domain times the volume of the domain. For double integrals, it was the value of the function at some intermediate point times the area of the domain. For single variable functions, it was the value of the function at some point in the interval times b minus a, the length of the interval. Okay? So this is IVT, intermediate value theorem for triple integrals. Okay? So this we know by Gauss, and now we can ignore the middle portion of this equality. So the surface integral over the sphere of radius r equals the divergence at some point q inside the sphere times the volume of the ball, of which the sphere is the boundary. Therefore, this leads to the definition. We can define the divergence of f at the point P, which we started with, as take the limit as r goes to 0. As r goes to 0, the ball shrinks as r goes to 0. R is the radius of the ball. R goes to 0. The ball shrinks. The sphere shrinks, right? And this point Q, which is some point inside the sphere, is forced to go to P, right? It's forced to approach P. And in the limit, you get P. So this is, at P, it's the limit as r goes to 0 of this surface integral, of the surface integral over SR of f itself, divided by the volume of VR. Or I can replace this, the volume of VR. I know exactly what it is, right? Okay, let's just leave it at this. It's the volume of a ball with radius r. It's 4 pi r cubed divided by 3. Okay? So this is the definition of the divergence at the point P. It's defined as a limit of surface integrals divided by volumes. It's, of course, a 0 over 0 sort of limit, right? Because the volume goes to 0, but so does the surface integral because the surface becomes smaller and smaller. Nevertheless, this is well defined. It's a limit, okay? And for this, it says nothing about the coordinate system, okay? So this notation is actually not a good notation to choose. I should have chosen this throughout, here and here and here. And now the definition is independent of the coordinate system, and in addition, doesn't require f to be C1. It requires f to be continuous, okay? Because the intermediate value theorem only holds for continuous functions. Okay, clear? This is a bit theoretic, but nevertheless, I wanted you to see this. So this is an alternative definition of the divergence, independent of the coordinate system. and not requiring f to be C1. What is important, and this is a comment that you should remember, so let's continue here. This definition requires only f in, not f in C1, requires f to be only continuous and is independent of the coordinate system. And you may think, who cares about the coordinate system? But this is maybe a second comment. The divergence, I'm not even going to write it because I don't want to confuse you, but you should remember this. The divergence takes different forms in different coordinate systems, in various coordinate systems. So for example, if you're looking at the cylindrical coordinate system, r, phi, rho, phi, and z, the divergence is not going to be dp to d rho plus dp to d phi plus dp to dz. That's not the divergence in cylindrical coordinates. It looks different. And in spherical coordinates, rho, phi, and theta, the divergence is not dp to d rho plus dp to d phi plus dp to d theta. It looks different, okay? And remember that, okay? I'm not going to give you the formulas. You can find them in the literature if you happen to need them, but just a point to be careful about. Okay, so that wraps up this comment. More comments about the divergence. Comment number 3. These are properties that I want you to calculate. It's not hard. The divergence is linear. So what do I mean by the divergence is linear? If I take the divergence of a linear combination of two fields, alpha f plus beta g, okay, and you know algebra already by this point, so you can think using algebra terminology. This is a linear combination of two fields, and this is an operator acting on the linear combination. And saying that that operator is a linear operator means that this should be equal to alpha times the divergence of f plus beta times the divergence of g. Okay? And you can verify this. This requires proof. Okay? In general, take f to be PQR, take g to be P1, Q1, R1, calculate both sides. You can do it and don't use the new definition. Use the good old Px plus Qy plus Rz definition and see that both sides turn out to be the same. Verify this. Okay? Here's another property of the divergence. Another property of the divergence. It's kind of so the divergence is some sort of derivative, some form of derivative, and it satisfies a property which is reminiscent of the product rule for derivatives. So what do I mean by that? If you take the divergence of a product, so what do I mean by a product? In this case, I mean a scalar function times a field. This is a product. So this is a scalar function. Let's write phi to emphasize this. So this is a scalar function. And this is obviously a vector field. And this is just the product of a scalar times a vector. So what's the divergence of the product? The divergence of the product is kind of like the product rule for derivatives, but we just have to set it in a way that it makes sense. So it's going to be the derivative of the first times the second. That has to make sense. So what's the derivative, in this case, this operator, of the first? Well, this operator acting on a scalar function is just going to be the gradient. So this is the gradient of phi. The gradient is a vector. I can dot it with f. So this is what we get for the derivative of the first times the second, plus the first times the derivative of the second. And this operating, acting on a vector field is, again, the divergence. Okay, so do you see, this takes some tuning to understand. Whoa, wait, what happened here? But if you think about it for a moment, you should see that this is kind of like the product rule. The derivative of the first, the only way to have this operator acting on a scalar function is the gradient times the second. These are two vectors, so saying times is going to be the dot product, plus the first times the derivative of the second. These are two scalars, so there's no operation here. It's just a scalar times a scalar. And the total of this thing is, of course, a scalar. This is a scalar, this is a scalar, and so is this. This is a vector, and the divergence of a vector is a scalar. Okay, is this clear? Okay. Another remark. By the way, many of these remarks, and this requires proof too. You can verify it. Okay, do it. Verify. It's an easy exercise, really, an easy exercise. Another remark. Suppose f is a scalar function. We can look at the gradient of f. The gradient of f, this is the gradient. The gradient of f is a vector. We can look at the divergence of the gradient. So this is the divergence of the gradient. And this thing is denoted, in short, you'll see it denoted like this. But the only way for it to make sense is this. And it's also denoted, another notation is by writing it like this. Changing the triangle, writing it like this again. And this is all the same notation, all notation for the same thing. And what it is the divergence of the gradient. The gradient, if you recall, is a vector df to dx, df to dy, df to dz. So the divergence of the gradient is d to dx of the first component plus d to dy of the second component plus d to dz of the third component. So it's d squared f to dx squared plus d squared f to dy squared plus d squared f to dz squared. This is what it is. And it's very useful in applications, and it even has a name. It's called is called the Laplacian. Laplacian. And named after a French mathematician called Laplace, also very famous. And it has a name because it's very, very useful. And moreover, here's another definition. Let's move to another board. Okay, let's write the definition here, and then I'll give you something else to practice on. A function f is called harmonic, a harmonic function, if it has a zero Laplacian. This is the definition of a harmonic function. Again, very useful in applications. I'm only touching these subjects. These are vast topics in physics and in electrical engineering and whatnot, and I'm only touching them, really touching and letting go because of our time restrictions in this course. So f is called harmonic if the Laplacian is zero. And what you can do as an exercise, so I'm going to give you something to just try and see if you can do the calculations. It's straightforward. There's nothing sophisticated there. You only need to write the details. So try and succeed. It's easy. There's nothing tricky here. Show that the function f of x, y, z equals 1 over the root of x squared plus y squared plus z squared is harmonic. So that the Laplacian is zero. Okay, and this is of course defined only for x, y, and z, which are not zero. Okay, so do this. This is good practice. Okay, the last comment I want to make is really of more of an intuitive comment, and it relates to the word divergence. So the one thing we hadn't said yet, we know why the notation is as such, but why is it called divergence? So when we say divergence, we kind of think of a diverging function or a diverging series or a diverging sequence. Why is it called divergence? So this would be comment number 6. Why divergence? And the answer, hey, we're on this board. Hello. No. Thank you. Why divergence? So the answer is, it goes back to the meaning of the divergence, which we discussed previously. So suppose we have a field that looks something like this. So I'm drawing the little arrows that represent the value of the field at every point. This is fun. I can do this for a while, but I'm going to stop since that's not the point. So suppose we have a field that looks like this, and here the arrows become even bigger. Oh, this is fun. You should practice drawing fields. It's really it's a good therapy. Okay, so here's a field. And suppose we put any closed surface somewhere in this region. So suppose we take, for example, a ball and put it here. Here's our surface S. Here's our surface S. This is a ball. what would be the flux of the field represented by these arrows through this closed surface? So the answer is, there's arrows coming in and there are arrows coming out, but as you can see by the length of the arrows, that the arrows coming out are bigger and longer. That should have been obvious in this picture. These arrows become larger and larger as we go out. So the arrows coming out are bigger than the arrows coming in. Okay? So the flux is going to be positive. And it doesn't matter where I put this ball, here or here or here or here, the flux through the closed surface is going to be positive. There's more of the field, of the flow of the field coming out than the flow of the field going in. Okay? So this field has positive flux. When can this happen? What can be an example of such a field? Well, for water, if the field is the flow of a river, this could never happen. If you take a ball and put it inside a river, the amount of water going into the ball, if the ball is made out of a net or something that allows the water to flow through it, the amount of water going in is going to be the same as the amount of water coming out. So this cannot be a phenomenon that you would see in a field which is the flow of water. This could happen, for example, if what you have is gas. If you're looking at gas, gas has this ability to expand. Okay? Gas can expand, and if this represents the expansion of gas, then you would get something like this. And this expansion, what you should imagine here, is the gas diverging. Okay? And positive divergence, which is precisely what's pictured here, is exactly this phenomenon. This is positive divergence of the field of F. Is it clear? This is why it's called divergence. Okay? And because it cannot happen, for example, with water, unless it could happen with water only if there's a source here. If there's a faucet here, then it could happen. If there's a source of the water, then it can happen. Okay? But in general, flow of water, the field representing flow of water, cannot have positive divergence if it doesn't have a source at the point you're looking at. And therefore, it's called, water has the property that it's incompressible. Okay? Gas is compressible. It can compress and expand. And a field with positive or negative divergence is called, what did I say? With positive, okay, I forgot what I said. So a field that represents water, flow of water, is called incompressible. Okay, and it has zero divergence, as opposing to gas, for example, which is compressible or expandable, and therefore has positive or negative divergence, depending on which direction you look at. And yeah, that's this remark, and that's the reason for the word divergence. Okay, that's what it measures. Okay. So this wraps up the additional comments that I wanted to say about the divergence. Again, I have to say this one more time. All these notions and all of this is really, really a huge part in applications. Okay, this entire course of Calc 2 is really just the tip, the mathematical basis for a much more expanded theory in mathematics and beyond mathematics, that if you take courses in physics or in electric engineering or in anything that uses partial derivatives in whatever engineering, I guess, you will encounter these notions a lot and work with them a lot. Okay, so that's the end of this clip.